Okay, this is chapter 9, linear momentum and collisions. So in this chapter we will see what is linear momentum, and we will apply that to collisions. We will also see the center of mass and the rocket equation. So first thing is, what is momentum, or rather linear momentum? In a later chapter we will see another kind of momentum, which is angular momentum. So momentum, the symbol is a lowercase p, and it is defined as the mass times a velocity. So if you have an object of mass m that's moving with a velocity v, which is a vector, we get the momentum. The units will be the units of mass, kilograms, and the v is meters per second. So kilograms meters per second, and this is what we call momentum. Now it's different from kinetic energy, even though sometimes people might confuse it, but it's very, very different. It is half mv squared. So you have a v squared here and only a v here, and also a force, which is mass times acceleration, which is m dv by dt. So it's a mass times the rate of change of velocity. So momentum is mass times velocity, kinetic energy has a v squared, and force has a rate of change of velocity. So these are all different things. Now momentum would be especially useful in problems involving collisions. It would be fairly hard to solve collision problems without the use of the momentum methods. This method primarily deals with, or is based on, what we call the law of conservation of linear momentum. Of linear momentum. This law says that in an isolated system, and isolated means that there is no external force on it. So in an isolated system, the sum of the momenta of the colliding particles, so if you have several colliding particles, you add all of their individual momenta to get the sum of the momenta of the colliding particles is before the collision, and that would be equal to the sum of their momenta. Momenta is the plural of momentum after the collision. So you add all the momentums of all the particles which are colliding before they actually collide with each other, and you add their momenta after they collide and move off in different directions, and the sum of the values before will be equal to the sum of the value that you would get after the collision. Or if we see it, a collision of two particles, if you have particle 1 moving with some velocity, and you have particle 2, let's say, it might also be moving with some velocity. This would be v1 and 2. Well, these are before collisions, and then after the collision, well, v1 would come here, v2 comes here, they hit off, and let's say m1 goes off in that direction, and m2 goes off in this direction. So this would be, well, let's write this as u1 to indicate it's before the collision, and v2 is after the collision. That would be v1 after the collision and v2 after the collision. Then this is the situation after. Okay, So this is the condition before the collision, the condition after the collision. Then the momentum, the sum of the two momentum would be P1 plus P2, that's before, and here it's P1 plus P2 after. Now we would write this as M1V1, M1U1 plus M2U2, and the same over here. Well, this would have an IJ component. We'll see how to deal with that in a minute. But let's first go back and sort of verify this law or write it in a mathematical form. So let's assume that we have something like this, and at the instant of collision, or as they hit each other, object 1 is going to apply a force on object 2, F12. Object 2 is going to be pushed this way due to object 1 at the instant of collision, and object 1 would be pushed in the opposite direction, which would be M21. So F12 would be equal to negative of F21, and that's from Newton's third law. So from Newton's third law, the force that 1 exerts on 2 is exactly equal and opposite of the force that 2 exerts on 1. And so we have this equation, F21 equals minus F12, or the other way around, and the magnitudes are equal and the directions are of 180 degrees apart. Now we can rewrite this equation as F12 minus F21 plus F21 equals 0, and then we write, knowing F equals ma, we write this as, this is the force on 2 exerted by 1, so it's going to be M2 A2, and this is going to be M1 A1. And now we know that the acceleration is dv by dt, so we write this as M2 dv2 by dt plus M1 dv1 by dt vectors. Now, because mass is constant, it can go inside the derivative. We can write it as d of mv2 over dt, and this would be d of m, well, that would be m2, m1 v1 over dt equals 0. Now mv is momentum, and therefore this can be written as dp1 over dt, and this is dp2, other way around, equals 0. Well, the result is still the same. This is 2 and this is 1. And this equation can be further simplified. D over dt p1 plus p2 equals 0. So what we get from here is that the sum of the two momenta remains constant because the derivative of the sum is 0. The individual momenta will change, but when you add the two changes, they become 0, or you can say that the change in p1 plus p2 is 0. And this is the law of conservation of momentum. Now, another way of looking at what we had here, we start from here, this equation has become this. So instead of writing as force as ma, we could have written this force, well, we could also do it from here, but we've already done all of that work, so we can write the force, which is ma, is the same as dp by dt. So force can be written as ma, and force can be written as dp by dt. So F is the rate of change of momentum. This is an alternate way of writing the second law. And it's useful when the mass is also changing, for example, in rocket propulsion. In those cases, it's better to use this equation rather than this, because here mass is constant and here mass may be variable or may be constant. Now, let's take this equation a little bit further, or this equation a little bit further, to say that the change of momentum is zero, which means, let's write it here, that P1 plus P2 is constant. And we'll use this for solving our problems. So by saying that the momenta before is equal to the momenta afterwards, we would say that the sum of the momenta initial is the sum of the momenta final. So the sum, if we bring this on the other side, the difference would become zero. So this is, if we have, let's say, two particles, mass would be m1 and m2, and velocity would be v1 and v2 and so on. So the initial momentum would be, this is a vector, so we can write it as a px in the I direction and a py in the j direction. And there would be a third direction also if you want to go 3D, but let's just stay with 2 dimensions. So we'll have this, and this would be before the collision, or initial, and that would be equal to pxi plus pyj after the collision, or final condition. So we could write it as initial condition and final condition, or before collision and after collision. This I sometimes confuses with this I, but when it's written outside the parentheses, it indicates the initial condition. So this is the I vector, and that's the final condition. Then this is the initial condition. That's the vector. Now, if we have two particles, well, there was a summation sign here. Let's suppose there are two particles, 1 and 2, and this is moving with some initial velocity, and this is moving with some velocity, and they collide, and they have some final velocities. So we write this out more explicitly, and we would write this as the sum of the momenta as p of particle 1 in the x direction and p of particle 1 in the y direction. So I and j, that would be their initial values for particle 1, and the second particle p2xi plus p2yj initial would be p1xi plus p1yj final, and p2xi p2yj final. So it seems like sort of complicated, but this is the initial momentum of particle 1 in the x and y directions, the initial momenta of particle 2 in the x and y directions, the final momentum of particle 1 in x and y, final momentum of particle 2 in x and y. Now, we don't add the x and the i's and the j's, so we'll collect the i's together and write one equation. So we'll collect these terms and say p1x, and we can skip the I, and p2x, these are the initial values, equals p1x and P2x final values. Okay, that would be an I and an I and I and I unit vectors. We can cancel out all the unit vectors because they're all in the x direction. So this is in the x direction, and in the y direction we would have P1y plus P2y initial. That's this one, and then that equals P1y and P2y final. So we're adding the two y components in the final after the collision. This equation is simplified to, since we're adding two components and there may be more than two particles, so we say sum of px initial equals sum of px final. So this term becomes this, and sum of py initial is sum of py final. So this is not the I direction, it's the initial. So we add all the initial momenta in the x direction and add all the final momenta in the x direction and make them equal to each other. So these are the two equations, and we can have a third equation also. Pz initial equals p sum of pz final. So these would be the equation that we can use. Now let's do an example on this. And here we consider a sort of a general case where we have the conditions before the collision are here and the conditions after the collision are here. So we have particle 1 moving in the x direction. Okay, we're trying to make it sort of simple. And we have particle 2 which will take as stationary, again, so that the solution is somewhat easier. So this will hit it on the edge and bounce off that way, and this will bounce this way. So after the collision, let's assume that particle 1, well, the arrow is too long, should be smaller than that, is moving this way, and particle 2 is moving this way. Now let's take some numbers, and let's say we will use u for the initial velocities and v for the final velocities. So that way we'll avoid the subscripts i's and f's, and it becomes a little bit more easier to write the whole thing down. So the initial momentum is going to be, well, we need an m1 here. So its mass is going to be m1, and this velocity is u1 plus m2 for mass of this one times the velocity of this one, which is going to be 0. And after the collision is going to be well, m1 v1 plus m2 v2 v1 and v2, because now they are both vectors in x and y directions. Here this was just purely x direction, so the y component was 0. So let's write them out in their x and y components. So on this side I'll write the initial, and here I'll write the final. First I'll write the sum of px initial equals 0. That's this term, so I'm going to write this equation. So px initial is 0, so I will write it's going to be m1, the velocity in the x direction, which is simply u1, plus the second term, which is m2 times 0, which is 0, equals, okay, there's no 0 here, px final, sorry for that. So the initial is here, and the final I'll write here. So this is the px initial, and the px final is going to be m1 times the x component of v, which is going to be v1 cos of this angle. So let's say that's theta, and x component of this one, which is going to be m2 v2, this angle is phi, cos phi. So we have an equation here, and this will be equal to this because these two are equal. Now it'll get a little easier if you take some numbers. So let's say this is 2 kilograms and this is 5 meters per second, and this is 3 kilograms and stationary, and v1, let's say it's 4 meters per second at 30 degrees, so this becomes 30, and this is unknown. So this becomes m1 is 2 times 5, 10, so the left hand side is 10, and the right hand side is m1, which is 2, and v1 is 4 cosine of 30, that's the x component, plus m2, which is 3, and v2 cosine of minus 5 because it's a negative angle, or you can take cosine of phi and say it's downwards. So this becomes 8 cosine of 30, which becomes 6.928 plus 3 v2 cosine of phi. Cosine of minus phi is the same as cosine of phi. Now we write the other equation, which is the sum of momenta in the y direction initial is equal to that of final. So here we'll add the py final. So that in the y direction there's no velocity, so it's going to be, let's write the equation first, m1 u in the y direction, and this is already zeros, and this is also 0, so it's going to be 0. And in the y direction here we'll have the v1 y, and here we'll have v2 y. So it's going to be m1 v1 y and m2 v2 y. Now m1 was 2, and v1 y is going to be 4 sine 30, and this is going to be m2, which is 3, and v2 y is going to be v2 sine of minus phi. So that's going to be 8, this is going to be 4 plus 3, no, it's going to become negative 3 v2 sine phi, because sine of negative theta is minus of sine theta, or you could simply say it's going downwards, so it has to be negative. So now we equate these, and we say 10 equals 6.928 plus 3 v cosine phi, that's the x equation, and the y equation is here 0 equals 4 minus 3 v2 sine phi. So we bring this on the other side, we subtract it, and we do the same thing here. And we get, from the first equation, we get 1.024 equals v2 cosine of phi, and from the y equation we get 1.333 equals v2 sine phi. So that's equation A and B. Dividing B by A, we get v2 sine phi over v2 cos phi is 1.333 over 1.024. The v2's will cancel, this becomes tangent theta equals, this ratio becomes 1.302, and therefore theta becomes tangent inverse of this, which comes out to 52.47 degrees. Now that we have the theta, that's a phi. So when phi becomes 52 degrees, therefore we can plug that in here. V2 cosine phi was 1.024 right in here, and V2 becomes 1.024 over cosine of phi. Plug that in here, and V2 comes to 1.681. Or we can use this equation, we should still get the same one number. And therefore, V2 is 1.68 meters per second at 52, or you can say at minus 52.4 degrees, or 52 degrees on the lower direction. Okay, so we have the solution, but we did need to know this in order to find this other one. If we did not know the velocity here, we would not be able to find the other one.